And we're going to start with Giovanni, whom you have heard from, and he's going to start with the toolkit of Almond.
Hello again, thank you for coming. I'm very excited to talk to you today about Almond, our open source collection of tools to build virtual assistant. And our goal is to support natural language programming. This is a framework in which every command gets translated into a formal programming language representation that makes use of APIs and skills in a library. And we care about natural language programming because it is powerful and it is useful. It allows you to connect multiple skills across different services. For example, I can say when I upload a new Instagram picture with a specific hashtag, post it on Twitter, and this in fact is one of the most popular skills on the if this then that website, connecting Instagram and Twitter. So why is natural language programming hard? We first of all need to design the skill library to support programming and interoperability. We then need to co-design the formal language to improve the translation. And finally, most importantly, and perhaps least unexpectedly, is we need a lot of high-quality training data. So our presentation is called ThingTalk, an encyclopedia of things. And Antapedia provides two things. It provides a uniform representation of APIs that, unlike the representation of APIs that are in Alexa or Google Assistant, which are mostly just intent dispatchers, we capture full signatures. We capture both the inputs and the outputs out of the APIs in static typing. And this enables us to have filters. It enables us to type-based filters, type-based composition or parameter passing. It also allows us to support interoperability as information from one API can flow into the next. In addition, ThingTalk stores natural language information. That is, it stores pairs of how you refer to a certain operation in natural language and the corresponding code. This is in form of annotations on the APIs, as well as templates that describe how operations are invoked. And I will go more into detail on the templates later. And our target language is ThingTalk. And here is the first construct of ThingTalk. This is when get do. It connects a when event, applies some filters to compute, optionally gets some extra data, and then executes an action. And we have chosen this construct because it is high level, it is useful, and it matches how our users want to specify this kind of very common, very useful commands. Not in particular compared to a regular programming language. It has no variables. Instead, you refer to names directly. It has no loops, and data is automatically iterated if necessary. And it has no if statements, which are replaced by conditions of the data in terms of filters. And given our ThingTalk language and ThingTalk API, it might be straightforward to understand a command such as this one, get the latest KCD comic and post a picture on Twitter. But when we apply it in the real world, the user might give us all these different ways to express exactly the same command, and we want to map all of these to the same code. So how do we translate all tasks to natural language? Training data is hard, and it is expensive to acquire. It is extremely expensive, in particular for the natural language programming task, because our training data is pairs of sentence and the corresponding program. That is, the annotation has to be done by someone who is a programmer, who can write code, and is an expert in the domain. Instead, we propose to annotate only a small sample of evaluation data, that is, validation, dev data, and test data. And we can then build a training set that doesn't include any real data. This makes it cheap, because we only annotate small data, and it also avoids the privacy problem because we don't need to continuously collect data from our users. And the way we do so is through our Genie tool, our Genie parser generator, that takes as input the ThingTalk information, the signatures and the operation templates. It takes as input the target language we're trying to translate to, that is the ThingTalk language, and construct templates that define how the language is used, as well as parameter data sets. These are data sets of like people names, locations, song names, and so on that are used for entity recognition. And out comes a trained semantic parser. So going into more details, our operation templates are pairs of small snippet of language, the part of speech, it could be a noun, a verb, a when phrase, and the corresponding code. And the interesting thing to observe here is that the same function, say list folder, can be used in many different ways. I can say to list my files, or I can use it to monitor when I modify a file, because the list changes, or when I create a file, there's a new file name. Further note that the same API can be referred both as a noun, such as the download URL of a certain file, or as a verb, just straight up download that file. And therefore, state-of-the-art technique that are based on associating a unique canonical form to each API or operation in the language are insufficient, because they wouldn't capture the whole variety of the way people interact with these APIs. Our operation templates are then combined into constructs. And constructs or construct templates are, again, pairs of natural language that are now grammar, not just a snippet, and the corresponding code, where the code allows the program, the template designer, to define how to program the training set and define how these constructs are combined. So for example, I can say, when I upload a picture to Instagram, then post a picture to Twitter, or post a picture to Twitter when I upload a picture to Instagram, and both should be recognized. And so our pipeline starts from the information in ThingTalk, the APIs and the operation templates. We combine them with the construct templates. These are defined once and for all for the constructs we care to support by an expert, a programming language expert, a developer. And we combine operation and construct templates to synthesize a very large training set. A small portion of it is then paraphrased using crowdsourcing, using mTurk. And both paraphrases and synthesized data are combined, augmented with parameter data sets that allow us to recognize entities to produce the final training data. And note that, unlike previous state-of-the-art, we train with both paraphrases and synthesized data. Synthesized data helps with compositionality. It shows that a certain API can be composed with all other different APIs independently, whereas paraphrase gives you robustness. It actually exposes you to different ways to express a certain command and teaches you language, fundamentally. We can also use the paraphrase and inspect it to build new constructs, which allows us to enrich the value of the few workers to put really a lot of effort to come up with creative sentences. And then we turn them into construct, and we can synthesize more data. And given the training set, we can train our model, which is called the LUINET, Language User Interface Network. This is based on the off-the-shelf DEC-NLP, or multitask question answering network. This is a model that was shown to be effective across a number of NLP tasks, uses both BiLSTM and self-attention, so you get the best of both worlds. And we have augmented it with a language model on the decoder side, taking advantage of the fact that we can easily generate a lot of programs because our programs are formal, and we can pre-train that part of the network. And moving on to our first experimental result, the first experiment is on this kind of when, get, do sentences. These are sentences that use one or two skills and at most two filters. And we ran our experiment out of what was the whole ThingTalk at the time, 44 skills and 131 APIs in American English. And we don't optimize on any skill specifically. We collect 1.3 million sentences with synthesis. We crowdsource about 1% of it, 24,000. That turns out to be $8,000. And after augmentation and training set is 3.6 million. For evaluation, we both crowdsource data from mturk that we then annotate manually, and we use data from the if, this, then that. This is data that we have no control over, and therefore is the most representative. As an aside, state-of-the-art previously would say test on paraphrase data. This, you should not do that, because in our experience, you can get near perfect accuracy on paraphrases, and then you deploy in the real world and the model fails miserably. And so we have split our evaluation data in a validation set that we use to refine our templates and build a better training set, and a test set that gives a final accuracy number. And without further ado, the result is that Genie improves over the previous state-of-the-art significantly. We can achieve an accuracy of 68% on the validation set, 62% on the test set. And again, note that there was no real data in the training set. This is all trained on synthesize and paraphrase and tested on real data. Furthermore, we did not optimize specifically on any skill. We just did 44 all at once with few students worth of effort. As a case study, we then put a few man days of effort on Spotify, and we can see that we can increase their accuracy all the way up to 80%. This shows that a domain expert that cares about can actually use this mechanism to improve the accuracy of their own skill. Furthermore, we applied Genie to an extension of the formal language. We added min, max, count aggregation operators to the language. And again, we find an accuracy around 60%. This shows that our models are extensible, and we can grow both the capabilities of the formal language and the ThingTalk collaboratively. And to put this into practice, and not just AI, we have also built a comprehensive virtual assistant engine. This provides dialogue management, skill configuration, and credential storage, as well as useful background services that most virtual assistants will need, like notifications, reminders, automations, and so on. And we have integrated with the best-in-class open source for input and output. We have used the Mycroft for voice, for hot word activation and text-to-speech. We use Microsoft Cloud for speech-to-text. We have integrated with the bot framework to give us access to Slack and a Messenger. And a member of our community actually built our integration with WhatsApp. Furthermore, we have shown that we can put this engine in Alexa and either use the native Alexa AI and just do whatever Amazon will do for you, or use our own AI and access our capabilities. And our engine runs on, we have a Linux version that runs on the cloud or runs locally on your computer or on your home server. The computer is how I run it. Or we have an Android version that runs on your phone, and in that case, all your credentials, all your API interactions happen directly from your phone. And so this completes our picture. You can see the Almond has grown a little umbrella because it's an umbrella for all these projects. We have shown the ThingTalk programming language, the Genie parser generator that allows domain experts to build their language capabilities. We have shown ThingTalk, our representation that enables this extensibility, and a LuiNet semantic parser, and finally the Almond engine. All of this is open source. All of this is modular. You can take any part of it, use it in your product, in your assistant, in your bot, any of it. And so our hope is that if you put your skill in ThingTalk, we will be able to access immediately all these existing assistants. Furthermore, because we have our own AI, you will be able to access Almond, the privacy-preserving virtual assistant. And because Almond is open source, we will be able to put it on websites, app, phone services, or anywhere you need a natural language interface. And my belief is that open source and open standard will win over walled gardens. Thank you. Do we have?
Is this like an intent error rate, or sort of choosing between different skills error rate, perhaps that you showed?
It's yeah, so our evaluation metric, because we are programming, it's program accuracy. We want to match exactly the target sentence. So all the parameters, all the filters, all the skills, everything has to be matched. We do in our paper have error analysis in terms of getting the skills right, getting whether it's a 1 or 2 element skill and so on, but we care about getting everything right at once.
So on the programming language that you're using, have you compared that with just using Sparkle? And what are the strengths and weaknesses of what you guys are doing versus that?
We don't have direct quantitative evaluation, but we have our experience. In our paper we discussed you need to follow certain design principles when you choose the target language. And a few of them I try to cover, including choosing a construct that matches the input sentence as much as possible. Because if there is a lot of change that has to happen in the neural network, it will be harder. You also need static typing and like an API, like a schema defined ahead of time, which in a graph database might be harder to obtain. You need canonicalizability, so you need a unique form for every program, for every semantic of the program, which kills out everything Turing complete, kills out Python, kills out SQL as it happens. So that's why we needed to design our own language.
The accuracy numbers, even though in general it seems like 60%, I wouldn't want to go to the doctor with 60% accuracy. But you're saying get every parameter right. So I'm hearing there's a shiny side of that, which is I bet you have high certainty of whether you know the query or not. Is that correct? So if someone could call you as a service and say, do you know this query? How much confidence could you return that you know the query and you got it right?
It's actually, unfortunately, the opposite. Because it is a generation problem, it's not. So in the classification world, people have done a lot to measure confidence, to measure auto-distribution, to bring these confidence scores to actually realistic values. In the generation, confidence tends to accumulate because you still have a language model at the end of the day. The language model, your confidence are driven by whether you're getting the grammar and the type right. And so it's kind of hard, and so it has basically 3 failure mode of operation. Either gets the right thing perfectly, it gets you something completely wrong, or it gets you nothing.
If you compare it with a lot of existing commands where they are just simple commands, then the accuracy is different. This is a lot of the compound commands with filters and so forth.
It seems like you would know like whether you covered the query or not. I mean, like you got a bunch of words here, and you got a bunch of parameters, and you laid them out, like you say it's a complex command. Normally you don't know. Normally if you just use a fuzzy probabilistic matching thing, you have no idea whether you got
Actually,
it right.
the direction that we are going is that we assume people will be breaking up their commands into pieces. All right, so there will be more like you say one thing that is easier to understand, and then you say the next thing. And the fact that we learn compositionality allows us to get to dialogues next. And I think that that's the better way to actually use this technology. But having a formal representation is really useful. I think that that's what we are trying to show. And you can even get to the 60-some% for these compounds with just a few students' effort.
Right, I think I might have to.
Yes, I think well, thank you very much.
All right, so hello. Like I said, my name is Paulus Schoutsen. I'm the founder of Home Assistant, and Home Assistant is the world's biggest open source home automation platform. It's around 6 years old. And the goal of Home Assistant is to create an open platform that puts local control and privacy first. It runs on low-powered machines that people can acquire. Like, for example, one of the main things people start with is like a $35 Raspberry Pi. You combine this with software that is free to download, and it's very easy to get started with Home Assistant. Home Assistant itself is like a Python application, but we have built like a small operating system around it that you can put on a Raspberry Pi, and it actually turns your Raspberry Pi into a full home automation hub. This allows users easily to stay up to date and stay secure. And with Home Assistant, we don't just actually target the United States and Europe, right? We work global, it's open source. And so we also made sure that we run everywhere in the world. And by that is mean, especially that, you know, a lot of people use phones, but the quality and the speed of phones across the globe is not as fast as we are like used to, especially like in something like here, like Silicon Valley. So we actually made sure that Home Assistant runs great on like budget Android phones. We also made sure that our user interface is fully translatable, and we have like support for 54 different languages in our UI, including like right to left languages like Hebrew or Farsi. You know, and this has made us very popular, right? Like, if you know, we don't have a lot of metrics just because we're like privacy focused. But if you look on, like, for example, something like Docker Hub, our installation has been, our images have been downloaded 10 million times. And so Home Assistant is like, is the community, and like the community is Home Assistant, right? There's no investors, right? The only thing we care about is users. And so at the end, we're like a group of people. We're building technology that we want to use ourselves. We're building technology that we ourselves want to run in our own homes, right? And at this point, at this moment, we're doing like a release around every 3 weeks, and we have around 85 people actively contributing code to each release. So this is kind of like how Home Assistant looks, right? It's an interface. You can put it on your phone. You can put it on big screens. It's responsive. It will scale down. It will scale up. And Home Assistant is built around 3 things. It's observe, control, and automate. Observe, we want to make sure that we know what's going on in your house. What is the temperature? Is the door open? Control, we want to be able to say, control the thermostat, control the lights, control the switches. And the third is automation. And automation is just a rule engine where the observations are the input and the control is the output. But to be able to observe and control things, we are the controller, but we are not like, we don't make hardware, right? We integrate with different APIs. And so we call these things like integrations, is when we integrate an API into Home Assistant. And we have around 1,500 different APIs integrated into Home Assistant. This ranges from like, you know, things like, you know, the Ecobee thermostat, Philips Hue lights, home automation protocols that like cover a wide range of devices like Zigbee and Z-Wave, and also low-level things like MQTT or like Arduino I/O pins. There's really no limit on what is possible. And most of these integrations, and this is what really makes us different from like all these commercial solutions, are actually maintained by the community. And this means that, like, you know, a developer starts using Home Assistant, maybe 7 out of the 8 things are supported, and he will add support for that 8th thing. Or maybe he starts using something, finds a bug, someone else reports a bug, and slowly we're creating like very solid integrations that has like very good support for like the APIs of the devices. And it's great because by doing this, we're actually showing companies that we care, that we want to control our own stuff. So for example, at some point we had an integration that was using an API that we observed from an Android application. And the company realized this, and then all of a sudden was like, hey, people want this, and they actually built an open API that allowed us to better integrate. And earlier I mentioned that we're like global, we're around the world, and it also means that we support APIs that are like from everywhere, right? So, you know, we have support for like DeepStack, which is like an AI platform from Nigeria. We integrate with like IoT products from New Zealand or India, you name it. So yeah, let's kind of quickly summarize like what Home Assistant is about, right? So Home Assistant is open source. Home Assistant available worldwide. We do everything local. Like the cloud is optional. If there's no internet, Home Assistant still runs. We store all the data local. We prefer local control. We will talk to the cloud, but then we just pull that data local as soon as possible, and that's where everything is processed. And we have a very layered, extensible architecture so that every piece in Home Assistant you can swap out for your own, you can customize, you can build on different parts of it. And then the other thing is that we have very like extended documentation on how our API is structured, how you can access it, and we have great ways for local applications to get like authentication and actually access this data. Right, so what does this lead to? So you get very affordable home automation, $35 or an existing computer, you're up and running. We get very fast home automation, because this is local, right? You don't have to go through a cloud, like your motion is sensed, it's like locally, we can control the light, locally. It's reliable, because there's less hops, there's less that can break. It is secure, your data never leaves your home. It's very customizable. We made sure that like everything in the interface, you can swap it out, and this is what we think is very important, because not a single person is the same, not a single culture is the same, not a single language is the same, right? We want people to be able to build user interfaces at the layer in Home Assistant that they want, or maybe like throw away our UI, build their own UI that is meant, that better fits their household, right? And the last thing is, we are a foundation for other projects. We have solved this home automation thing. Like, we know about we know about the data that's at home, and we allow you to control things at your home. And by being open, we allow other projects that want to build something with smart home data to just use that data. They don't have to reinvent the whole wheel. They don't have to build all their own 1,500 integrations to get started. And this is kind of where Almond comes in, right? Because Almond reached out to us recently, and they were like, "Hey, let's talk." And I was looking at their website, and it's like, we're open, we're privacy focused. I'm like, that's us. But we only really focus on the smart home. We don't have the assistant, we don't have the natural language processing, all these things. So this was a perfect match. And so we started our teams teamed up and we started hacking together. We built an integration both ways. So the first thing that we did is that we added Home Assistant support to Almond. So anywhere where you are running Almond, and like Giovanni said, you can run it on your phone, you can run it at home, you can run it anywhere you want, you will now be able to control lights or any other device. But then, of course, for Home Assistant users, that's not useful, because then they need another app, and they kind of want to have everything at once. So we also added support to Home Assistant to directly, inside Home Assistant, talk to Almond. And so now I'm going to do a live demo. Okay, so for this demo, I'm going to just open 2 Home Assistant UIs. And the reason for that is that once I'm opening Almond on here, it's like an overlay, and so you're not going to be able to see what's happening. So I put the left screen. It's in sync. Everything in the Home Assistant is always streaming, so everything's always in sync. As you can see, something changes, it's immediate. So the first test always, when I'm testing Almond, if it works, is to ask for a joke. So let me see. I don't have audio output, but that's okay. We don't need audio. Okay. That's okay. It's on the screen as well. Tell a joke. All right, that works. That's great. So now, of course, you also want to control Home Assistant, right? So turn on the lights. Ta-da. Okay, that worked. That was great. So what's happening here, this is actually running in Chrome. So Google offers for websites integration with Google speech-to-text and text-to-speech. So we can just leverage that. But of course, that's not a great way to expose Almond, right? Because then you have to open your app, open the UI, and you can actually already just touch the buttons that you want to touch. So we have some ideas around that. But the first thing is what we want to do is that we want to improve Almond. Because right now, the way we do things in open source is that we build out the foundational, the backbone of these integrations, and then the different devices or different utterances and the skills, we leave that to our open source contributors. Because these are small tasks that people can pick up in the weekend. And so one of the things is that Home Assistant supports a lot of different things. And this is a bunch of the things that we support. And these things are not yet supported in Almond. So one of the things that we want to do is that we want to make sure Almond knows about them, knows which piece of information these devices have, and be able to know which controls these devices have. So for example, a light, you want to be able to say, can I turn on and off? But you want to change the color, the brightness, the light temperature, right? It gets complicated very fast. The other thing that we're going to do for Home Assistant is that we're going to, right now, I have Almond server running on my computer. But that's not very convenient. That's not what I can ask my users, just install this server and then you can connect it all up. So what we're going to do is that we're going to make a way that users will be able to press a single button. It will install Almond. It will configure Home Assistant to talk to Almond, and it will configure Almond to talk to Home Assistant, all with a single button click. That way our users will be able to get started very fast. However, like I said, that's UI. That's a good step, but we want to do it better. So then we were thinking is what is a voice assistant, right? Like when we talk about like speech to text, it kind of basically boils down to this. You detect a hot word, you start throwing speech to text, then you try to get the intention of this text, then you do something with that intention, and then you speak the response back to the user. And so we are like building a voice assistant, a generic voice assistant add-on for Home Assistant. So what does this mean? So we're just gonna plug in pieces of technology. So for hot word, we're just gonna go off with Snowboy for now, because there's no good open source hot word available that runs on a Raspberry Pi. We're gonna do speech to text, conversation is gonna be by Almond, and text to speech. And this text to speech and speech to text, these are all integrations in Home Assistant. So people will be able to plug in different things, people will be able to experiment, and this will allow to like kind of like plug and play your own assistant. And as long as it will, we will make sure that it works out of the box. So the idea is that like, you'll be able to install Home Assistant, plug in a speaker and a microphone into your Raspberry Pi, and have your own voice assistant. And this too is actually something we're going to launch in like 3 weeks. So that's Home Assistant. Thank you. Are there any questions? Yeah.
Quick question. Do you already run the Almond parts on the Raspberry Pi?
Yeah, so that's a good question. So right now we run the Almond server on the Raspberry Pi, but the Almond server will still communicate with the Genie cloud, I think it's called, Giovanni?
Yeah, the inference side of Genie.
Yeah, so the way Almond works is that the text to ThingSpeak will happen in the cloud, and the execution of the ThingSpeak with the connected accounts will actually happen locally. So right now, what our first version is that we'll just send it to the Almond server to just convert it to ThingSpeak, and the ThingSpeak will be executed locally. Yes?
So is the iPhone, is it accessible for the iPhone yet, or do we need to wait until so you've got it on Android?
Right now, Home Assistant is a web application. So you can run it on your iPhone. We also have a native iPhone application to integrate with Home Assistant. The biggest downside is that like the systems are pretty locked down on Android and iPhone, so we couldn't do like a hot word detection that routes to us, right? It will end up in Siri or Google Assistant. But if you want to have your iPhone open it up and control your house, that's totally possible.
I meant the Almond voice assist.
Ah, okay. Oh no, so you can talk to just type to the voice assistant through your iPhone, but you will not be able to speak. Yes?
Considering you're processing so much locally, I'm really curious, basically, are there really notable differences in performance, in the usability based upon the hardware utilized? Is the smartphone really offering any discernible difference than a high-end desktop?
I think so. The reason why it's pretty easy to run home automation at home is that there's not that much data at home going on, right? Like how often do you open a door? How often there's sensors, they will generate a lot of data, right? The real powerful things that consume a lot of resources is if you start dealing with video, right? If you're gonna do either just video streaming, if you start doing machine learning on video, like object detection, these kind of things, that's where we start running into limitations of hardware, and that's where I see that the users that do that with Home Assistant, they actually upgrade. They no longer use a Raspberry Pi. They will have servers running. And nowadays there's these Coral sticks from Google that they can offload a lot of machine learning, and actually those work pretty well as well with Raspberry Pi still, but it's a little bit more complicated to set up. Yes.
Do you see a world where your Home Assist can plug into something like Comcast or AT&T or one of these larger home security systems?
I think, in the end, if there's an API, either public or at least accessible, we can plug into it. And generally, these things happen is people will have these systems and then they're like, I want to use this. The odds, however, that somebody would pay for Comcast and for Home Assistant and then make that bridge is probably pretty small. The biggest challenge that is actually in the IoT space is that there is no standard. Right, I know the Mozilla guys have been really working hard on the Web of Things standard, but adoption is not really there. The bigger players don't really care. If you look at like the Google, the Amazon, they build their own standard, and we just have to send them all our data. And that's not something that like really works for us. Cool, thank you.
Thank you. Very good, thanks. So our next speaker is Silei, and he will be talking about the queries using with natural language, the queries on web.
Okay, hello everyone. So we know question answering is one of the most common uses in virtual assistants. So in this talk, I'm going to talk about how Almond can answer complex queries on the structured web. So I believe people in this room are all very excited about how virtual assistants have been growing in the last couple of years. And just last month, Alexa announced it reaches the 100,000 skills milestone, which is really impressive. But still, this is only a tiny portion of the data out there in the web. In comparison, there are 1.7 billion websites, so we still have a long way to go. And further, with a much more flexible user interface, linguistic user interface, virtual assistants need to be able to answer all kinds of questions from users. And sometimes these questions can be complicated. For example, it's totally natural for me to ask, what is the top-rated Chinese restaurant in Palo Alto? But such a simple question, in fact, involves 3 different properties and computation on top. So how can we build a QA system that can scale up to the level of the number of websites, and at the same time handle the complexity here, complexity in questions like the examples here? So we present our toolkit called Schema to QA. It can generate QA system for all websites as long as they use Schema Dog, and it can answer questions, complex questions with multiple properties and computation. And last but not least, it is cost effective. So we can do all domains in Schema Dog automatically, and developer can put in a small amount of manual effort to improve the performance in each domain. So in our experiment, we reached about 75% of accuracy with just 1 man-week of effort for one domain without any real data. So how can we do that? And as have been introduced multiple times, we use natural language programming. So we turn each question into a ThingTalk program. So we don't rely on the actual information on the website when we parse in the natural language, and then we just run the ThingTalk program to query the website directly. So now let's first take a look at how we can use ThingTalk to represent complex questions. So in its most basic form, a ThingTalk query comes with a table and filters. So for example, we can filter on the restaurant table on the property serves cuisine. So this will give me Chinese restaurants. And we can put on more filters. For example, I can limit location to be only in Palo Alto by filter on geo. And we also support sorting. So I can sort, for example, I can sort on the ratings. So this will give me the top-rated Chinese restaurant in Palo Alto. And we also have support for joins. For example, I can join the restaurant table with the review table. So this will give me restaurant reviewed by Bob only. And on top of that, ThingTalk also have support for projections, so users can get the particular property they care about. We also have support for aggregations, so we can calculate the min, max, count of different properties, and there's so many more. So this shows that we can use ThingTalk to represent the questions, but where can we get the data? So as we said, we use Schema Dog. So Schema Dog is a way to store structured data on web pages. And it's mainly used for search engines nowadays. And it covers a lot of domains already, from restaurants, hotels, to recipes, products, news, and so many more. And here's an example. We grabbed it from Yelp. This is information for the French Laundry restaurant. It contains the information of the restaurant, including the name, the cuisine, the rating values, and so on. And most importantly, there already 40% of the websites using Schema Dog. So it would be great if you can use Schema Dog to retrieve information. But Schema Dog is designed for machine, not for human. So we need to somehow map Schema Dog to natural language. So we have developed a tool to automatically translate Schema Dog into our Antapedia representation with, along with all the natural language annotations for each property and operation templates. Due to time limit, I'm going to introduce one component in this tool. So as you can imagine, one of the most important and challenging tasks is to understand how each property can be referred in natural language, and they vary very differently between different properties. For example, let's look at two properties in restaurants, service cuisine and rating value. So probably the most common way we refer to cuisine of a restaurant is just by its value. We'll just say Chinese restaurant without mentioning the word served or cuisine at all in the sentence. The fact Chinese is a cuisine is just implicit. But this won't work for rating value. If we only use the value, we'll generate something like 4.5 restaurant, which doesn't make sense at all. So as you can see here, there are a lot of ways we can combine the value, the property name, and the restaurant together in natural language, but they just won't work for every property. So to solve this problem, we use the actual data in the website. We collect a sample of the value for each property, and we generate a lot of combinations of the value and the property name and the class name. And then some of these candidates are bad, some of them good, but it's okay. We throw all of them into a search engine, and we rank by the number of exact matches. In this way, we learn which combinations are more common to use in real life. And then we can pick the top ones as our operation templates. So in this way, we can generate very reasonable operation templates for our Antapedia representation. And we also allow developers to further fine-tune the templates manually to improve the performance. So at the end, we're able to translate the entire Schema.org into our Antapedia representation, along with all the natural language part. So now, by leveraging the abstract schemas in Schema.org, we're able to have access to 40% of the websites. But note that due to the time limit and the resource limit, we only crawl data for 3 domains, so the search engine approach will only apply to these 3 domains. So now we have the Antapedia, which gives us the function signature, the natural language annotations, the operation templates. We can now use Genie to generate a large training set to train LuiNet. So now we can finally finish this diagram, beautiful diagram of natural language programming, to turn the questions into ThingTalk. So now let's move on to see how the system actually performs in real world. So we first test on 2 domains, restaurant and person. Restaurant, we use data from Yelp, and person, we use data from LinkedIn. And using Genie, we generate a training set of 1.8 million sentences for restaurant and 900,000 sentences for person. And for evaluation, we collected another set of more realistic data. We went to Mechanical Turk and give Turkers a list of properties they can use and just ask them to come up with whatever questions they want. So this is as realistic as it can get. And one interesting thing we noticed is that we only ask for questions with 1 property or 2 properties. But however, in restaurant domain, we still get a lot of questions involve more than 3 properties. This is probably because some of the questions are just too natural, and the Turkers themselves didn't even realize that they're using so many properties. So let's take a look at the result. So overall, we get 74% for restaurants and 78% for person. And on the questions with only 1 property, we're able to get 80% for both domains. And for questions with 2 properties, we still be able to get over 70% for both domains. And I think most impressive thing here is that for questions with 3 or more properties involved, we can still get 65%. And keep in mind, all these numbers are trained without any real data. So this provides a very strong baseline for QA systems. And this high accuracy benefits a lot from our templates. So we have a very comprehensive template set in our Genie and in our ThingTalk representation. So, in fact, if we train only on synthetic data, we still be able to get like between around 40 to 50% of accuracy in these two domains. And in comparison, if we use the templates in previous work Sempra and only training only on synthetic data, the performance will be really poor. And we also explore that how the knowledge can be transferred across domains. So we did an experiment on transferring knowledge from restaurant to hotels because they share a lot of properties. And we put zero effort, manual effort to the hotel domain. Except the evaluation data, we collect the same hard, realistic evaluation data manually. And we didn't even do paraphrase. We used a script to transfer the paraphrase data in the restaurant domain into the hotel domain automatically. And yet, we still get 55% overall accuracy on hotel questions. And if we only count questions using the shared properties, we get 63% of accuracy. So this means that the knowledge we learn from one domain can be easily transferred to similar domains. And last, we also integrate the schema to QA in our Almond assistant, of course. So these are two screenshots we captured just to show it works from end to end. So in conclusion, we present our toolkit schema to QA. It can scale by mapping schema.org to natural language, and it can handle complex questions, and it is cost effective. So every company, websites can use our tool to build a QA system themselves. Thank you.
So using the exact match is a very interesting idea on the web search engine. So my question is, why don't you use a language model? So a very simple graph can also tell whether this.
Right. We actually thought about it, and we want to implement it in the future. It's in our roadmap. Yes. Yes.
So in terms of generating the natural language description of the program, so you use a web, and you mentioned that you were able to map the entire schema out to the natural language side.
Yes.
So, but I wonder, so I think the schema should contain a lot of long tail entities that doesn't occur very frequently on the web. So did you have any problem collecting descriptions for those?
So for the experiment we did for the 3 domains, we trimmed down the ThingTalk representation to only the data we have, only the data we crawled from the web. But we are able to generate the entire schema.org, but the quality might be not as good once we have the data. So, but that's fine. But because if you don't have the data, it's not meaningful to generate the question anyways. It won't give you anything. So we assume that the data is always available in our setting. So if people apply our tool, they will have the data to refine the natural language annotations and operation templates. Yes.
I just have a quick question. So with our implementation, the W3C Web of Things is not standardized yet. There's an approach to use like IoT.schema.org for these JSON descriptions, but it's not far from complete. However, the Web of Things description in the JSON does have these links, you know, so Mozilla's implementation of everything our gateway can handle could be, you know, pulled in and parsed. And if you have that data, then you get over the problem like Paulus mentioned, where all the manufacturers of the devices don't actually, you know, make things easy to integrate. We have to like transform all of them into a standard rather than every light bulb having common, you know, characteristics. So if you had that smaller data set of like an IoT.schema.org, could you run it all as part of this, you know, just the way you've done this standard schema.org framework?
Yeah, it's definitely true, yes. So, I mean, it's both the IoT, the Home Assistant abstraction, and schema abstraction give us the ability to like map to a smaller basic abstractions to be able to handle a lot of more devices and web pages. So I can definitely see that happening if we have that in Schema Dog.
Yeah, because ours is all exposed with one web thing API. We hide all of the brand specific
Right,
stuff.
right, definitely. Yes.
So what is it going to take to increase the accuracy?
So here everything's automatic. the part that we find increased accuracy most importantly is the natural language annotations for each property. For example, we have a lot of heuristic and algorithm to generate them, but still sometimes it's not accurate, not complete enough. So for example, serves to saying, for example, rating value, when we refer it to in natural language, normally we'll use the word star, a 4-star restaurant or something like that, but we cannot generate that from nowhere because that information is not in any form in the Schema Dog. So by manually putting those information will give us a boost in natural language translation.
Thank you very much.
Let's see. I'm going to go through kind of quickly, and so I'm mostly talking about I'm entirely talking about the open source and academic Snorkel project that we've worked on for about 4 years out of Chris Ray's lab here at Stanford, and through my PhD work as well as that of many of my former lab mates and current coworkers. So I'm going to give just a very high-level overview, and there's a lot more that we actually just did a release in August, right after a workshop we had at Stanford of the V0.9 with a bunch of new tutorials and stuff like that. So you can go there for more. Or talk to me over lunch. Once you've taken your first bite, I'll answer theory questions. Okay. So I'll start with the motivation, and again, this is going to be somewhat high level, and we've worked on all sorts of applications. A lot of this stuff actually has been deployed, or sort of versions of this system, I'll say, have been deployed in actual production, virtual assistant systems out in industry. But broadly, I'm going to talk about how do we train a classifier or some kind of machine learning model. You can imagine mapping a classifier to what's the intent, or what device is the user asking about, or something like this. But I'm just going to stay very high level. So a lot of our motivation, this is not an exclusive statement, but it's based on our observations over the last 4 years, is that machine learning development, if you think of this supervised setting as having kind of 3 basic ingredients at a high level. You have training data, you have some kind of machine learning model, you have a model class or a model architecture that you need to tune on that data, and then you have some kind of hardware to do that training and serving. And it used to be, certainly when I entered grad school here, that if you just built a model for one particular, type of X-ray or type of natural language task or one type of hardware, algorithmic implementation, still quite an accomplishment, but that would be, like several PhDs worth of work possibly. And now for a lot of tasks, we can actually just take, robustly supported open source components for the models, and there are lots of, other platforms for the hardware, and get these things running at least to a first approximation on traditionally grand challenge tasks like text, natural language, image, etc., in like several lines of Python. You can guess my punchline. This is all predicated on the on having a training data set for the particular task. So we've seen a lot of use cases and kind of see training data as one of the in a negative phrasing, the key bottleneck in ML dev today, and the positive phrasing, the kind of differentiator that decides whether and how well an application works. So I'll just give one example that I can share openly from a radiology project that we have ongoing. I think it's on its like seventh submission right now, but it's kind of at this intersectional niche of systems and radiologists. So it's still going out there. But the numbers were kind of staggering in that we looked at basically how much variance we got in an end performance metric. This is ROC AUC on a binary triage task at the over 4 radiology and neurology data sets of the Stanford hospital system. Just a classification problem. Basic point was that it took a couple days to try everything from an AlexNet to a DenseNet, ResNet, sort of 7 years of deep learning image model progress. About a point of difference in ROC AUC. Whereas it took about 8 person months of a Stanford radiologist's or a team of Stanford radiologists' time to actually label a training set. And if you look at the curves, you look at the differential from, say, a couple weeks to a couple of months of training data, so the volume, you look at the noise level of the training set. I'll get more into that. And you look at the data augmentation strategies used, which was mentioned earlier, all about an order of magnitude larger effect on the end performance. So this is just a caricature of many settings we see where this is the lever that ML engineers actually want to be playing with. Not that it has to be an either or, but this is the kind of differentiator. Either way, it's the one that we're excited about. So just to highlight this, labeling training data sets by hand is fine if it's cats versus dogs, or if it's stop signs if you're doing AV, or some settings maybe for general natural language understanding. But for many settings, it's very expensive when you need to have domain experts actually do the labeling. It's very difficult when you have privacy constraints, right? We work with many people, both academic side and through other routes, where you can't ship data out to be labeled on the government or medical or tech side. And finally, every time you enter a new setting, so your input data changes or your output goals change, what you want the model to do, you often just have to relabel the training set, right? And I can get into that with some case studies. The key idea that we've pursued for the last 4 years and are still working on along with a lot of others in the community is trying to build and manage training data programmatically. Or rather, from the perspective of us as system builders, we're trying to build a platform, Snorkel, that enables people to build and manage training data sets and thereby kind of program machine learning models programmatically using higher level heuristics. So just to situate, the goal has always been not to kick the human out of the loop, but to let the human interface at a higher level rather than labeling individual data points, writing heuristics, putting in their domain expert knowledge in higher level ways. Okay, so I'll give a concrete example just to start. This is just a canonical one of machine learning, a classic binary classification example. I actually don't know enough about home loans to know on my own whether this was spam or not. So I guess I would have been a nice mark, but apparently this is spam. Our goal is to put into a model, and model just says spam or ham, yes or no. It's classic machine learning application. So the high-level question or one of them that motivated us, phrased another way, is, why is hand labeling the only interface to much of the machine learning stack? Right? I have domain expertise. For example, if I think that the phrase money might be highly correlated with a spam email, I may have what we often, in a recent paper with Google, called organizational knowledge, which could be on the open source, on the web, or it could be inside your organization. I might have a list of drug names, and I know that if it matches that list, that's a good sign. It's often called at a high level distance supervision. I might have a legacy model. That's not good enough for various reasons, but I think that if it labels something as spam, that's indicative. But all of this kind of gets thrown out. Instead, we just pay people to individually label data points. So in the idea in Snorkel, and these are just different components of a current deployment version that we're building, but the high-level point is in all these papers and in the open source repo. We want to kind of go through 3 main steps. The first is that we try and let users directly express knowledge as functions. So there are actually a bunch of operators, but labeling functions is the first one. Training data needs to be labeled for a classification task. So rather than having this just come through in yes/no labels, we let them write what we call labeling functions. So this one is a simple one. Just says taking a data point, if money is in the body, labeled as spam, else abstain. And you can think of different ways of doing this. We have GUIs that we build for certain deployments. You can just write Python in the open source. We've done a recent paper we did directly from natural language to labeling functions to then training a model, a system called BabbleLabel that was presented at ACL by my lab mate. Either way, all of these different sources of labels come in, and then a lot of the work that we did over the years, especially on the theory side, was figuring out how can we combine all of these noisy sources. So you write 20 labeling functions, and any data point is labeled by a couple of them, and they disagree, and they may be correlated or have different levels of accuracy on different subsets or partitions of the data. How can you automatically learn where to trust the different label sources and how to not double count them if they're correlated? And so we've done a lot of work on doing that in an unsupervised or sort of latent variable modeling fashion over the years. I am way too happy to talk about that later. Ask someone about their PhD thesis at your own risk. But anyway, and then done a lot around the data management aspect of this. Is if your training data is being generated programmatically, there's a whole bunch of new things you can do around managing, monitoring, versioning, and serving it. And the final goal, in general, is to then use this programmatically labeled data to train some machine learning model. A question that is a natural one to ask is, why do you even train the model if you have a bunch of functions that label data? It's a good question to ask, and the answer should ultimately be answered empirically, which we try to make easy to do in the open source code. But the basic answer is usually the machine learning models of today are quite good at generalizing either to more features or to new feature sets. So you can write labeling functions over, say, the text of a radiology report, but train an image classifier that can now recognize the incoming image without the text. Or you can write a bunch of these rules over natural language and have the machine learning model automatically generalize to synonymous phrasings or terms. And what are the advantages of this kind of programmatic labeling approach? And I'll just say this quite openly of, not Snorkel versus others, but just sort of weak supervision in general is the usual umbrella term that's, of where this work has fallen. Well, first of all, you can, get training data much more quickly. You can dump in signals from across an organization. Again, that could be, dictionaries and models found on the internet or inside your org. You can do eyes-off labeling to a large extent. You can usually need to look at some data to write these labeling functions, otherwise like flying blind. But then the majority of your data set can be labeled by a program rather than by a human. So we can drastically reduce the number of eyes that need to go on data points. And if your ML model is not instantly perfect after it comes down from the deep learning heavens, then you can actually go back and iteratively tweak your training set until, especially on, we've done work on specific slices of data to actually get it to work, especially as conditions change. So I'll just breeze through. I'm actually going to skip some of these. So these are all published. Google was an interesting one because I think there's upwards of 25 deployments that at least I'm aware of now. But we started with 3. And a lot of the motivation here was that there's actually a lot of budget for labeling training data, but because of privacy expertise and most of all adversarial nature of the problems, where it changed a lot, they were having to relabel all the time. So it was actually even for them a pain point. Recently presented about an Intel deployment, the Stanford hospital I mentioned. I'll just show one result here, which is kind of cool. This is an RSC AUC curve. So up and to the left is better. This is a triaging application. So this is just taking in, say, a chest x-ray and just saying, should this be bumped to the front of the queue to be read by a radiologist? No replacing radiologists in the problems we work on. Or can this sit in the back of the queue? Urgent or not, a triaging problem. So this is the line after person months of hand labeling. This is a recent paper that was published by a collaborator after person years of labeling at Stanford. Then we had an interventional radiology fellow at Stanford Hospital write about 20 labeling functions, and that took him a couple days, and this was the RSC-AUC curve there. So a brief note on this. From one perspective, this is kind of an eye-popping result. Months, nearly years, going to days. If you look at how we did it, it's actually fairly low-hanging fruit. A lot of the images had these messy text records. We wrote these labeling functions over the text records, got noisy labels that Snorkel used, rather than having a radiologist sit and look at the images. So this isn't meant to be magic. It's meant to just, grab the low-hanging fruit of how we can often label data in programmatic and more efficient ways. Okay, I'll briefly talk about, should I cut now?
I think last sentence.
Last sentence. Okay, well, I'm going to skip by. Then this is the actual superglue. If any of you are familiar with superglue, it's a natural language understanding task. Has more relevance to voice assistants. I'm going to skip by and just say that I'll end on this slide. If you're curious about anything that I just talked about and not ready to murder me out of hunger, or actually the latter one, maybe that subsides and you go back to being interested. We actually have a range of other operators, and we did a lot of work to extend the open source code to support them. So it's not just labeling data, but we've, over the last 4 years at Stanford, looked at what our collaborators are doing to actually get models to work on the training data. So these include 2 others that we recently started supporting. One is a data augmentation. So the canonical example is rotating images before you feed it into your model. Any image model uses it. Increasingly, text natural language models use it as well. That was based on 2017 work in NeurIPS, and it's supported in there. And then we have a recent paper in NeurIPS in 2019, so this year, about what we call slicing functions. This is actually motivated by a real-life Snorkel clone deployment at a big technology company with a big, well-known voice assistant, where, as well as other applications, where certain slices of the data were really critical not to mess up on. So we have a new paper on how to actually let users noisily specify those by writing little functions, and then have the model automatically devote more representational capacity to trying to do well on those slices. Anyway, thank you all for the time.
Michelle is a sophomore, and she's going to take 5 minutes to tell us about the hackathon that she is running. That is going to help.
This will be the fastest presentation you've ever heard. Yeah, so like Monica said, I'm a sophomore undergrad, probably the youngest person in this room, and I also didn't get the memo to dress in dark colors. Sorry about that. I'm just going to talk about TreeHacks. So TreeHacks is something I'm involved in, and essentially Stanford's hackathon. I'm going to go through a few slides, but this year's TreeHacks is super excited to partner with Stanford Oval to make voice assistance hacks as accessible as possible. And some background for what exactly TreeHacks is. Let's go back to what a hackathon is. Hundreds of hackers from around the world gather and build something they're passionate about. TreeHacks is Stanford's student-led hackathon, where we bring 1,200 plus hackers last year. This year we're looking at about 1,400. We bring those hackers to Stanford for 36 hours to work on some awesome projects. So, like I said, the number of participants we have over half of them are Stanford students, 8 plus countries, 86 plus schools, and for all these students, we fly them out, we provide all travel reimbursements, all food for the entire event to make sure the event is as accessible as possible. Last year we had 50% female and non-binary admits, and we had 41 prizes for these hackers who made the best hacks. This year, the reason we decided to partner with Oval is because we know that students feel there's a need for a privacy-centric open source voice assistant platform. And what does this look like in terms of providing, this assistance to students? Well, in one way, we want to provide resources for hackers. So that takes the form of hardware, from Raspberry Pis to smart home assistants that they can hack off of, APIs, data sets, industry mentors, both technical and non-technical. We have tech talks, hands-on workshops, and prizes for hackers to have the best experience possible in 36 hours. From here, we hope that hackers will be able to improve Almond's natural language understanding model for those who are more machine learning focused. We also want them to implement new capabilities on ThingTalk, to use hardware to customize virtual assistants, and so much more. And what we found is every year, these hackers really surprise us. So there's no predicting what they can or can't do. We just want to provide the resources to make sure they have all the ability to make that happen. Let's take a quick look at past voice-related projects. Some super cool ones that we've had in the past is, one was a voice assistant to engage citizens in diverse, healthy political discourse. Another was a safety-oriented virtual assistant that interacts with and guides users walking alone at night, and that's also able to send emergency alerts. And the last one I think was super cool as well, a memory tracker skill for Alexa that uses sentiment analysis to categorize and store memories for the user to reflect upon in the past and to track mental growth. So these are super cool projects. We have more that I couldn't fit on this page, but for some context, that's what we're working with in terms of the hackers who are interested in this space. And these are from past TreeHacks. That's when we didn't even have specific focus on voice assistants. So with this year, when we're deciding to funnel a lot of resources into that, we're excited for all the possibilities. Yeah, so for the benefits of TreeHacks in terms of sponsors and companies, one of the biggest is company brand awareness. Because you bring, so many engineering-focused students all into this one event, you get a lot of company brand awareness within 36 hours. The second one is code contribution to innovative ideas from hundreds of the world's brightest engineering students. When you have, a dedicated 36 hours for students to really use their brains and think of, whatever crazy ideas they can, you get some really exciting stuff, and that's been awesome to see from this past year. And the last one, classic, recruiting. Yeah, that's pretty self-explanatory, I think. Yeah, so the core of it is by supporting Oval, you're also supporting TreeHacks and the growth of hundreds of top engineering students across the world. And I think it's super exciting that voice assistance is such a rapidly growing platform, and that students at Stanford are so excited about it. So I think when you harness the talent that you get from students, the bright minds, and also the existing platforms out there, you get some really awesome projects in the works. So yeah, I did promise I'd be fast. Thank you so much for your time. Come chat with me if you'd like to be involved, if you're not too hungry, and definitely feel free to email me at baom@stanford.edu if you're interested in getting involved. Thank you so much.